Hello, my name is Andrei, and together with my colleague Sergiu, it is our pleasure to present to you our paper for DVCon U.S, which is entitled, as you can see on the screen, UVM Feedback Loop, the Foundation of Self-Improving Testbenches. This paper is based on a previous framework that we presented at DVCon EU, and which I'm also going to shortly explain in this presentation. And our purpose is to create a certain set of automation scripts that can help the engineer finish project faster and with much less effort. This paper will primarily focus on a script we created, which is aimed at optimizing coverage closure, but instead of using methods that were tried in the past, and instead of focusing on certain algorithms that might not be general enough, we are just going to focus on how this framework that we created can help you to basically apply whatever algorithm is fit for your block to be able to automate the coverage closure part of the project. Also, all of the code that we have available, the framework together with all of the scripts and with all of the testing we've done for them and a user guide and everything else will be available to you. We made it public, it is uploaded to GitHub, and a link for this will be presented at the end of this presentation. What we are going to cover in this presentation is first a short introduction that is going to go over the guidelines and the architecture that is required for all of this to be possible. This is basically the code that we are going to provide. We named it AMIQ ECTB, which stands for AMIQ Externally Controlled Test Bench. It is a framework that enables you to create test benches in a dynamic way. Basically, all of the components that you have and all of the scenarios that you have created, the test cases, they are going to be controlled from outside of the simulator at the moment we are just using one I/O method, which is +args, but we plan to basically include everything that can be used. We are probably also going to maybe make some testing to see which one is faster. When it comes to this framework, I'm going to, as fast as possible, go through it, basically show some code examples and some use cases, and explain how it is being used and what are its pros and if there are any cons, which certainly are, but we hope that the pros are going to very much outweigh the cons. I'm also going to show how this framework can be used when it comes to automation, and explain how this feedback loop can be established, which is basically having an externally controlled layer enables us to have certain scripts that can parse the coverage databases of our previous regressions, and we can modify how our environment works and how the test cases behave. And I'm going to showcase some examples, talk about some results that we've seen, and also go over the conclusions. So the current I/O method that we use for providing this externally controlled test bench layer is +args, but it can be replaced with minimum changes in the code by anything like reading files and creating JSONs exactly for this reason. An example here for an environment that is controlled through +args can be seen on the slide. In this case, we are trying to showcase that you can always have a hybrid environment. Basically, if you have components that you always know that are going to be there, like scoreboards or coverage collectors or any other things that are always going to be instantiated no matter what, then they can be hard-coded just as usual, like create a normal system Verilog UVM test bench. But there might be certain components, like let's say certain instances of VIPs that can be scaled up or down. So let's say you have 10 ports, but in certain test cases you only run on one port. So then you don't want to create all of the VIPs if you are not going to use them. So in that case, you can scale it down by telling the simulator at runtime to pass to the test bench a variable that tells you exactly how many components should be built. And this is exactly what our framework provides. It's an infrastructure that gives you this control over the test bench. And this is not only for the components. This was just an example I used. It can be done for any variables, including how many sequences are created, how to schedule them, what constraints to apply to them. I'm basically going to show how to control any object or component creation and how to modify the variables inside them, which is everything you need to fully control a test bench, an environment, and any test case that you want to create. With everything that was said so far in mind, we want to present a certain way of working for a verification project using this framework, in which there are one or more engineers creating backend code, as we call it, which is basically the functionality of the test bench, and then there is one or more front-end engineers that create the scenarios using the backend code. In this case, we present a way of creating scenarios by writing them in an Excel spreadsheet, because as we said, plustars are just text files, so you can write exactly what sequences you want to run and what constraints, what flags, everything that should be basically randomized in those sequences. And through a script, this can be translated to a text file that can be passed to the simulator, and in this way you can have your environment collections if you use multiples, and also all of your test cases. As I said, the architecture itself is not enough. We also have to have a set of rules. I'm not going to go very in depth in this. This was presented at DVCon EU and the time is quite short. So I'm just going to say that everything has to be dynamic. So you have to stay away from hard-coded connections between different instances or between sequences. Each sequence, if you control the scheduling from outside the simulator, has to be able to be instantiated at any time and have no prerequisites when it comes to connections. Basically, you cannot throw a handle to a component that might not exist in the sequence. So all of these connections, they have to be done, let's say, through UVM config database, which imposes other restrictions. The first code example that I want to show is a component. This is the same as an environment, so they both exist, AMIQ CTB component and AMIQ CTB environment. They contain a number of functions, which I'm not going to go in depth here. They can be found in our user guide, which allow you to basically create any number of components dynamically. On the right of the slide, you can see an example on how an environment can be created dynamically. As you can see, any number of components can be created of any types, and they can be assigned any names, which can be later used to parse through the array of components that have been created, because they are going to be pushed in an array, and you can cast them to their relevant types based on the name. If they exist, of course, because you can choose to define them or not define them. Under the pictures, you can see the paths at which the code can be found in our library. On the future slides, I'm not going to include that, at least not for all of them. But what's important on these first ones is that under SV in the AMIQ CTB library, you can find the code that you have to import to be able to use this framework. And under TB, you can find the examples and the testing we've done for this framework. Going further, I am going to showcase how an environment extended from AMIQ CTB looks. If we look on the left side, we can see that there is a post-create components, which is a hook that is available in the base object. It is extended, and we have this cast agents and configure agents functions. So basically, from using plustars, we can create any number of components, but they are all going to be part of the same array, which is components. As you can see in cast agents, we go with a loop over the entire array, and based on the name of the components, we cast them to some relevant types. This is just an example we used. You don't really have to do this, at least not at this point. If you want to, for instance, not compile them, then you don't really have to use the instances directly in the environment, but we choose to use this as an example because it is much easier to understand. Of course, those agents have to be configured as well. So here we see that we can create the configuration objects statically. We don't have to create everything through +args. So we showcase this to see that a hybrid model is possible. While the configuration objects are being created statically, we do want to be able to control what's inside those configuration objects. Because the number of configuration objects can vary, we can create a global environment configuration that can tether to the maximum number of agents that can exist. In our case, we use this environment configuration object, and we have seen that, or we have chosen that for our test bench, we are going to have a maximum number of 5 agents of each different type. And we have 3 different VAPs that we've created as a model. And here you can see that one of the rules on some slides ago was that everything has to be registered through +args. What that means is that register all vars function has to be done in each object or component for each of the variables that have to be able to be controlled at runtime. In our case here, we put all of them. I didn't put everything on the slide because, well, you can see that it's 5 of each, so it's a lot of variables, but I wouldn't say it's such a big work for the reward that you get. In our case, again, we are doing this statically. This object is not being created through our framework. It is created directly in the test bench test case, and it is being passed to the environment through a static connection. This is possible because we know that the environment will always exist, and we always know that we are going to have this global object. So you can, as you can see, you can have dynamically the components that can be omitted, and you can have statically connections for the ones that are always going to be there. Another big difference, and probably the most important for this particular paper that we're presenting today, is the capacity to use text inputs to create scenarios. So on the left side, you can see the run phase at the top, the run phase from the basic component that we provide in the library that you have to extend from to use this. And at the bottom, you can see just the run phase of our test bench test case, the one showed on the previous slide, which just calls super. It raises objections, and we just added a function that helps us track performance, which collects the system time. On the right, you can see a scenario, which is basically just 3 sequences that are going to be seen on the next slide. And as you can see, they have like a name, they have a parallelism status, which is that _p that can be seen on the second and the third sequence. And of course, because all of the variables inside the sequences are defined as +args through that register all vars, all of them can be controlled. So basically we control all of the constraints on the sequence dynamically, which means we can use scripts to generate these inputs, and we can create thousands, millions of test cases instantly to be able to reach any verification needs that we find that are necessary. So, capitalizing to everything that was said so far, I'm going to basically explain why this paper is named how it is. So, by having this mechanism of controlling a test bench from +arg files, which are basically text files, we are able to create an initial set of +args, which is our basically test bench and all of our scenarios as they are in the, let's say, first phase of closing the verification, and we are going to start to run regressions. Now, these are going to give us certain results, and based on those results, we have to update the sequences and their constraints to be able to maximize the coverage output. Now, In certain cases, of course, you have to add a new functionality. There is no way around that. You are going to have to modify the code. But when it comes to the final stage, when you are just trying to fill in coverage, most of the time what you do is you run a regression, you see what is not filled, and then you either increase the number of packets on certain test cases, or you modify some intervals on some constraints, or you modify some weights, or you just add new scenarios based on the existing sequences. And all of this is controllable through text files when it comes to plusargs and when it comes to our framework. So all of this can be automated because there are, and we are going to present one as well, there are a few tools as open source on the internet that can parse WHICHES databases, which is the standard for coverage databases. And that's how feedback loop can be established. You use the coverage to modify the inputs to the test cases, which basically modifies the behavior of the test cases or creating new ones. Extrapolating from the figure that was visible on the previous slide, we can apply this recursively when running regressions. So instead of running a regressions, looking at the results and then modifying the inputs for the next test case, and by inputs I mean the constraints of the sequences or even the sequences that are being run. In this case, we are using a tool, and we are going to provide an example and of course, again, an open source tool that you can use to parse the WHICHES database and generate a readable file that contains the results of the regression. Based on those results, then they can be parsed by a script that contains a certain algorithm that makes the relation between the coverage and the constraints that have to be applied to the sequences. And then based on that new constraints that have to be applied, a new plusarg file is generated and a new regression is being run. And this can be repeated until the 100% coverage milestone is being reached. Going a bit more in depth, as you can see on this slide, so we start with the coverage database, which can be seen on the lower right corner of the figure. That one, it goes through a tool that is able to parse WHICHES databases. In our case, we use something that's called Coverage Lens. It's a tool we developed in the past at AMIQ. That tool is going to generate a JSON file, which will contain all of the coverage results in both a human and machine readable format. We are going to merge that with the results of all of the previous regressions, right? Because we want to basically be able to converge to the 100%. In our case, we also use such a big randomization space that you wouldn't really be able to fill coverage without merging databases. Also, an important thing is this will be increasingly more efficient if you break, let's say, a full regression that you normally run into smaller regressions, because you would be able to update the plusargs sooner. So after merging them, they are being passed to the script, which is going to basically see if the end condition is being met, if all of the coverage has been collected, or if not, it's going to update the plusargs to better target the coverage that hasn't been achieved yet. And this, of course, goes to the regression manager that you use, and another WHICHES database is produced, and this cycle repeats. As I mentioned, I'm going to leave here a link. I think all of the slides are going to be available, so you should be able to click on them. This is just a tool that is able to generate much more workable format for a coverage database. It is open source. I think we maybe changed it a bit, so it might need an update based on the compared to the version that's available online. But yeah, I wouldn't say this is a necessity. There are other WHICHES database parsers online. I'm sure you can find one. I think the most popular one is called something like pi witches or something like that. So getting back to how our script is supposed to work, basically we run a regression. We don't change the constraints at all. We see what the results are. And then on the following regression, based on the results, we are going to change the intervals and also increase and lower the weights of certain intervals. So we allow the randomization of the simulator to more efficiently explore the space available for the variables that are involved in the coverage scenarios. And of course, subsequently, we keep changing them. They can be reversed as well. So you can see I'm going to do a short explanation on how you can vary between completely random and some more targeted test cases. The scenarios that we used for our testing, we have two cases. We focused on the first one because we believe it's the most unfavorable and like the hardest challenge that we can get, which is when we have a very, very big randomization space. In this case, it's 2 to the power of 96, and we have minimum, maximum, and mid values. The number of mid intervals we try to vary. I think in this example, the code here are about 8,000 bins in a cross. So as you can see, we have coverage on 3 different fields. They have the minimum, maximum, and the mid intervals, and all of them are crossed. And this is red. If you remember from previous slides, we also have blue and purple. So we have 3 times 8,000 intervals in a cross. This is something completely insane. It's way above anybody would ever face in a real project. The second case, the one which is very favorable for our script, is where you actually have complete scarce values. So basically, in the first case, we do have the low and the high, which are going to be very hard to cover in the cross, but we also have the mid intervals, which is being crossed with the low and the high. So in this case, the entire space of the variables is actually being used. In this case, you can actually alternate between complete randomness and also directed test cases. So you can get the best of both worlds. So a directed test case, when you know exactly what you have to do to the randomization to reach those cases, it's going to be incredibly simple. The challenge that you have to face is that you actually have to be able to define an algorithm that makes the translation from seeing the coverage uncovered and being able to produce some constraints that are going to fill that coverage. Because in certain blocks, this can be quite a challenge. For case 1, basically the algorithm for was very simple, because as I said, we are trying to basically provide and give you a framework that can allow you to set up your own algorithms and make this translation from coverage to inputs. We are not going to exercise with complicated algorithms, and I don't think there is an algorithm that can serve the purpose of all of the blocks. In our case, what we've seen is when you actually have coverage that is spun across the entire interval, for the first, let's say, I don't know, 90% of the coverage, I'm just taking an arbitrary number. I think you can probably just run one regression, and the first one has to be completely random, and then you can actually speed it up by using the script. But up to a quite high number, there won't be very many changes, because there are still a lot of values that haven't been covered in all of the 3 values when you are looking at the cross. So then already the randomization algorithms that the simulator provides, they are quite efficient at exploring the space in a reasonable manner. So modifying the weights, modifying the intervals, you are not actually going to be more efficient than the way the algorithm is actually spreading across the entire randomization space. But when you go above 90%, when there is a lot of things that have already been hit, here is when you actually have to make sure that the coverage is converging. Because in our case, you run let's say 3 regressions, you get a very good coverage, but you run 30 more and it doesn't improve that much, because that is the problem when you have such a huge randomization space and you have a very big cross. The best way or the best approach that we have found for this solution is to actually greatly reduce the number of intervals and the weights and increase the weights for the ones that haven't been covered, but track it as a function of the delta coverage from one regression to the next. And this is basically how you get the best of both worlds, because you keep the constraint random, but also you make sure that the coverage increases steadily in the last phase of the verification project, and you don't actually get stuck running regressions and always getting the same coverage. So finally, what we are working on is we want to give better I/O possibilities, so maybe +Rs are not suitable for everybody. We haven't yet run like performance test cases to see which method is the best, but definitely even at this point we wanted to have both being able to just read text files and have +Rs, which I think are the two best ways of giving external control to the test bench. We also wanted to do some testing with some other popular coverage parsers. And we also want to do some improvements to how these algorithms are being applied to our script, because you have to come up with a basically function that translates coverage to constraints. So for the conclusions, as you can see, like the framework from the examples I've shown earlier, it's very easy to adopt, and I think that is like the key of creating a new innovative way of doing verification. Is you cannot just go wow and create something that's huge, because it will never be it will never spread. People don't want to spend a lot of time to be able to adopt a new solution. And yeah, like what we chose to do to be able to improve our processes is this higher layer of abstraction, which is something that has been seen before in the verification world, which PSS tried to do, right? It is a higher abstraction layer over any kind of verification, any kind of test bench, I would say, right? Any kind of verification anywhere on the verification hierarchy. But we believe that the delivery that they had, so far at least, it's been not so good. And of course, what we can highlight is that we don't see any problem with using System Verilog and UVM, even though the projects we're working on currently, like simulation takes a couple of days. And finally, of course, so we have our blog where we basically released this. We posted an article when it was released, and mainly the information that was in that article can be also seen in the user guide, which is uploaded to our GitHub, for which you have a link right here on the slide. And this was it for me. Thank you for watching, and good day, good night, or good morning.